Hello, this is Mr. Filsick. Today we're going to be exploring the less than essential question, how are the frequency, wavelength, and speed of a wave related to each other? First, let's look at frequency. As you'll remember in your notes, frequency is defined as the number of cycles that are completed every second. For example, let's look at this picture here and imagine that this is a picture of 5 different waves, each after 1 second. Up at the top, we see 1, 2, 3 waves, 1, 2, 3 waves in 1 second, or 3 cycles per 1 second. Down at the bottom, we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 waves in 1 second. Which one has the higher frequency? The one at the bottom, the purple one, because the waves pass by more frequently, if that helps you remember it. Another way to remember it is just when the waves are closer together like this, they have a higher frequency. Let's make this small again. Whenever we talk about frequency, the wavelength we use, whenever we talk about frequency, the unit we use will always be hertz, H-E-R-T-Z, and we'll abbreviate it Hz, hertz. Next, wavelength. When it comes to wavelength is maybe a little more simple to remember because wavelength is just the distance between 2 identical parts of a wave. So either from the crest to this one to the crest of that one, crest of this one, crest of that one, or we could measure from the trough of this part of the wave to the trough of this part of the wave. That's the length of one wave. A wavelength is measured in meters because it is a unit of distance, just like we've talked in the past. And lastly, we're talking about speed. Speed is pretty simple. It's just the velocity or the speed at which a wave is moving. So speed is measured, just like we measured velocity in the past, in meters per second, or abbreviated m per s. The formula for the speed of a wave is speed equals frequency times the wavelength. Now this formula might look pretty funny up here. So let's talk about what each variable represents. V represents the speed of a wave, or you could think of it as velocity, if that makes it more simple. F equals the frequency, which makes sense, right? The most difficult one is this variable at the bottom. This is a Greek letter called lambda. I'm just going to write this in parentheses so you know how to say it. Lambda, say it with me, lambda. And it is used to represent, you guessed it, the wavelength. So you see the formula is speed of the wave equals frequency times the wavelength. The formula for speed of a wave looks a lot like another formula we've looked at so far. Do you know what formula that is? Velocity equals frequency times wavelength. It's set up just like the formula for work. Work equals force times distance. In the last unit, we talked a lot about the relationship between force and distance. Because frequency and wavelength are set up in the same way in their formula, the same can be said about them. Just like force and distance are inversely proportional. Frequency and wavelength are inversely proportional. In other words, as one goes up, the other goes down. As one increases, the other decreases. As frequency increases, wavelength decreases. It makes sense if we think about it. Let's draw a wave right here. And let's draw a pretty high frequency, right? The waves are pretty close together. Let's draw a low frequency down here. The waves are a little farther apart. What you'll notice is that when there's a high frequency, when there are a lot of waves, quite naturally, the wavelength is going to be shorter, right? Down below, when the frequency is lower, there aren't as many wave cycles, the wavelength is going to be bigger, right? So as So we're seeing a very easy illustration where when the frequency is large, a lot of waves, the wavelength is small. When the frequency is small, the wavelength is big. They are inversely proportional. Now to start applying these formulas we've learned, move on to the next videos that will explain how to solve for speed, how to solve for frequency, and how to solve for wavelength.